now we'll find the expression for the thermodynamic potential Helmholtz free energy, which is denoted by F. So to find that, let us consider a system which undergoes a transformation from initial state I to final state F. And during that process, the temperature of the system remains constant at T. That is, the process is an isothermal process. That is, during that process, the temperature remains constant. Now, during this isothermal process, suppose the heat exchanged between the system and the surrounding is delta Q. And change in internal energy delta U is delta U, which is UF minus UI. So UF is the internal energy at the final state, that's why F, and UI is the internal energy for the initial state, that's why I. Okay. So what is the corresponding change in entropy? So corresponding change in entropy delta S is, it will be entropy at the final state SF minus entropy of the initial state SI. Okay. So now we will apply Clausius inequality. So we know from Clausius inequality that delta S will be greater or equal to integration dq by T from initial state I to final state F. Okay. So from Clausius inequality we know that change in entropy for any process delta S is greater or equal to integral of this quantity dq by T from initial state to final state, where you know this inequality sign holds for the irreversible process and the equality sign holds for the reversible process. So now we know what is the value of delta S. It is SF minus SI, which is greater or equal to, now since the process is an isothermal process, the temperature T is constant. So that's why this 1 by T temperature will come out of the integration. Then we have integration I to F dq, or SF minus SI greater or equal to, now what is integration I to F dq? It gives us the total amount of heat which is exchanged between the system and the surrounding during this transformation from I to F, which is, we have stated that it is equal to delta Q. That is, in this process heat exchange between the system and the surrounding is delta Q. So that's why this integration I to F dq will be equal to delta Q. So it will be delta Q by T. So we can write, since integration I to F gives us the total amount of heat exchange during this process I to F, which is delta Q. Okay. Or now what we will do, we will bring this T on the left hand side. So we will have T SF minus SI greater or equal to delta Q. So now we will put the value of delta Q from first law of thermodynamics. So we can write from first law of thermodynamics, we know that delta Q is equals to delta U plus delta W, where delta W is the work done in that process. So putting this value of delta Q in the equation. Suppose this is our equation 1. Okay, so let us call it equation 1. So now we'll replace delta Q from the using the first law of thermodynamics. Okay, so now putting this value of delta Q in equation 1, we get on the left hand side we have T into SF minus SI, which is greater or equal to delta U plus delta W. Or next what we'll do, we'll bring this delta U on the left hand side. So we have T SF minus SI minus delta U greater or equals to delta W, or T SF. So now we'll remove the bracket. Okay, so now T will be multiplied to both the terms. Okay, so T SF minus T SI minus, now we'll put the value of delta U. So we have already defined that delta U is UF minus UI, greater or which is greater or equals to delta W. Or so now what we'll do, we will write the terms at the final state together. Okay, so it means that so first we'll take the terms for the initial state. Okay, so this TSI, this term and this EY term, we will write them together. Okay, so EY is the internal energy of the initial state, and T is constant for throughout the process, so it is same for the initial state and the final state, and SI is the initial entropy of the initial state. So we'll write these two terms together. So if we remove the bracket, so this EY will be plus, so minus and minus plus. So we have EY and this is minus TSI. Okay, we are writing this together. Then we will write the rest of the term, that is the terms for the final state, which is this one UF, which is the internal energy of the final state, and this TSF. Okay, where T is constant. Okay, same, and SF is the entropy of the final state together. So if we want to write them in the similar form, U minus TS, so we will have a negative sign. Then because it is minus UF, so within bracket we will have minus UF minus TSF, which is greater or equals to delta W. Okay, so here you see we have minus minus plus, so EY minus TSI, EY minus TSI, then we have minus UF, so minus within bracket UF, and this is plus, so as we are writing within the bracket with the minus sign over here, so it will be minus TSI. Okay, so here you see they have a similar form. It is EY minus TSI for the initial state and UF minus TSI for the final state. So now we will introduce a new function. So introducing a new function F equals to U minus TS. Okay, so U minus TS. So what will be UI minus TSI? So it will be Fi. Fi will be UI minus TSI, meaning this is the value of the function for the initial state, and this new function F for the final state will be UF minus TSF. Okay, So the value of this new function f for the initial state is fi, which is ui minus tsi, and the value of the new function for the final state f is f, which is uf minus tsi. Okay, so if this is our equation 2, so now from equation 2 we have so instead of ui minus tsi, we can write it now fi in terms of the new function f, and then uf minus tsf we can replace it by ff, the value of the new function f for the final state small f, which is greater or equal to delta w. Okay, so now the value of the new function at the final state minus value of the new function f for the initial state is delta f, which is the change in the new change in the new function f in the process I to f. Okay, so it is change in f in the transformation I to f. Okay, change in f of the system, if I write. Okay, so therefore from this equation we have, so it is fi minus ff, so it will be minus delta f. Therefore fi minus ff, which is minus delta f, because delta f is ff minus fi, so fi minus ff will be minus delta f, which is greater or equals to delta w. Okay, so if I write again, delta f is okay, if I write fi minus ff is equals to minus delta f, so from this equation we get that if this is equation 3, then minus delta f will be greater or equals to delta w from equation 3. So, or if I rearrange it, we can write delta w is less or equal to minus delta f. Okay, so just writing delta w on the left hand side, this sign will flip and it will be delta w less or equals to minus delta f. So it means that, so delta w is the work done in the process, and if you remember, the process was isothermal. So this delta w, the work done in the isothermal process is less than or equal to negative change in this new function f. So we can write so since, if I write it again, since delta w is less or equals to minus delta f means negative change in the new function. So we can write, thus work done delta w in an isothermal process, because this process, the transformation from I to F is an isothermal process, is less than or equal to negative change in the new function f. Okay, according to whether the process is irreversible or reversible. So if the process is irreversible, then the work done will be less than, and if the process is irreversible, then the work done will be less than, and if the process is reversible, then the work done will be equal to negative delta F. Okay, so we can say that this new function f is called Helmholtz free energy, and it is defined as F equals to U minus Ts. So it is one of the thermodynamic potential which is defined as F equals to U minus Ts, where U is the internal energy, T is the temperature, and S is the entropy of the system.